for our last set of videos in 1.2, we're going to talk about a couple of weird limits and a couple common trick questions. So we're going to start with what I'm going to call example 4, which is the limit as x approaches 0 of the absolute value of x over x. So the easiest thing to keep in mind here is that, so we're going to talk about what this visually looks like, and then once we talk about that, I'm going to be able to show you why this limit does not exist. So, so here's the thing to keep in mind. So let's actually talk about what an absolute value is fundamentally. An absolute value is actually a piecewise function, right? A piecewise function is just a function that behaves differently for different inputs, right? If you input a positive number into an absolute value, you get the same number back out. The same thing happens if you input 0 into an absolute value. So let's talk about this absolute value of x for a sec. It's actually a piecewise function. If you input x values that are greater than or equal to 0, you just get an x back out. So if you put in a 5, absolute value of 5 is a 5. You just get the same value back out. But if you put in values that are less than 0, meaning negative, you get the opposite of that negative number. So a negative of that negative number, meaning negative x. So fundamentally, the reason that's relevant is that this graph is going to be piecewise. It's going to behave in two different pieces. Okay, so this graph, which can't actually have a definition at 0 because you can't divide by 0, this graph is going to behave like a negative x over x, which would just be a negative 1 for x values less than 0, and like an x over x, which is just 1, for x values greater than 0. Notice I took out the equal to because you can't divide by 0, okay? So what this graph is visually going to look like is on the left of 0, it's going to be a horizontal line at negative 1, and on the right of 0, it's going to be a horizontal line at 1. And there's going to be a jump discontinuity. And we're going to talk a lot more about discontinuities in 1.4, but there's going to be a jump discontinuity, which means, so for the record, the limit as x approaches 0 from the left of this thing would be a negative 1. See, left limit, negative 1. The limit as x approaches 0 from the right of this thing would be a regular 1, which means that this guy does not exist. But the reason I said it's a common trick question is when I look at this problem, if I see this as a multiple choice question, my brain's like, yo, that's DNE, because it's going to be this jump discontinuity every single time. Now, if there had been a minus here, like approaching from the left, well, then it would exist. It would be a negative 1. And if there had been a plus, it would exist. Now, there's always a couple of people that are like, but Hogan, really, why would you go to piecewise functions? You're a monster. And I get that. So let's say that you were just completely and totally over this, and you're like, listen, man, I'm not doing that. Here's a funny, easy way you could deal with it. You know you can't plug in 0 because you divide by 0. So you could say, hey, I'm going to pick a couple really easy numbers on either side of 0 and see what happens. So I could pick negative 1 and negative 2 on this side of 0, and I could pick 1 and 2 on this side of 0. If I plug in, when I plug in a negative 2 in the absolute value, I'm going to get regular 2 over negative 2. Oh, look, it's a negative 1. Regular 1 over negative 1. Oh, look, it's a negative 1. So from the left, I'm clearly approaching negative 1. They're all going to be negative 1s. And if I plug in 1 over 1, I'm going to get a 1. And if I plug in 2 over 2, oh, look, it's a 1. So from the right, I'm definitely approaching 1. So if you're just completely over this concept of a piecewise function, and you're like, listen, I know this is a trick question. I'm just not about this life. I'm not splitting it into some crazy piecewise function. You could just also make a table of it around 0, right? So if you want to try P4, it's slightly harder. It's going to be a DNE also, for the record, but because of the same jump discontinuity. But if I put a plus or minus, then this would be a different question, right? It would be some other number. So I'm going to walk you through it. If you want to pause me and do it on your own, that's fine, okay? So my argument here is that if I clean up the bottom a little by factoring out a negative 3, I get an x minus 2, right? So I'm going to argue that really what I'm looking at is a negative 1/3 in front of the same exact problem we just saw. Now sure, it's x minus 2 instead of just an x, but notice that if I plugged in the 2, I'd still get zeros. So I'm going to argue that I essentially have a negative 1/3 in front of the same trick problem I saw, and that because this is a jump discontinuity, it's going to be DNE. if you wanted to split this into piecewise functions, you could arguably make this a negative 1/3 times that negative 1 for x values less than 2, and a negative 1/3 times the positive 1, just like we saw the last time up there when I made the piecewise function, right? Because this would be negative x minus 2 over x minus 2 for x values greater than 2. And then sure enough, what you're going to find is that this guy is a 1/3 and this guy's a negative 1/3. So the left limit's a 1/3, the right limit's a negative 1/3, so it does not exist. It's going to look like this. Here's 1, so that's a 1/3. And here's negative 1, so that's a negative 1/3. So see how there's, oh, sorry, that's, I put it at, come on, Hogan. I put the jump at 0. It's not at 0, it's at 2. Come on, brain. Okay, so it's going to have a jump at 2. All right, so that's one way to do it. The other way to do it, if you're like, Hogan, I hate you, why would I do that, is to do exactly what I did up here, which is center your table at 2, pick a couple easy values on either side of 2, and see what happens if you plug in, right? And you can plug in the original. You can be super lazy about it. If you plug in 0, you're going to get a positive 2 on top of a 6, which is a positive 1/3. If you plug in 1, you're going to get a positive 1 on top of a 3. Oh, look, it's a 1/3. So on this side, oh, look, it's a 1/3, which is totally what I got here. So the left limit is a 1/3. And on the other side, if I plug in 3, I'm going to get 1 on top of a negative 3. And if I plug in 4, I'm going to get a 2 on top of a negative 6, which is totally the same negative 1/3. Oh, look, my right-sided limit is totally a negative 1/3, and my limit does not exist because of the jump. So, common trick question. If it's ever a double-sided limit that you're asked for, you can go ahead and say it does not exist. Okay, let's talk about oscillating limits that don't exist. So, there are a couple different ways that a limit cannot exist. So we've already talked about a few of them, right? Fundamentally, the two big ways a limit cannot exist, right? So if a limit does not exist, there are a couple big ways it can, okay? Number one, the left limit doesn't equal the right limit, right? And if that happens, then there's no double-sided limit, right? So we just saw a couple of examples of that. Oh, look, that's a jump. Left limit doesn't equal right limit. Limit does not exist. Now, your textbook in 1.2 is actually going to tell you that if a limit goes to infinity, it doesn't exist, and I'm going to argue that that's actually not true. That they're going to argue, and I don't agree with it. They're going to talk about unbounded limits, right? Because they're going to tell you that a limit means you go to a finite number. But the trick is that in 1.5, which we're going to do in a couple days, they kind of reverse this. So they reverse this statement. And they say, oh, yeah, you can have limits that go to infinity. So we're going to kind of ignore that unbounded thing. And if you want to look at what they're talking about with unbounded things, you'll see it on page... Sorry, sometimes I'm a little slow getting to the page I want. You'll see it on page 50. So one of the reasons I'm not going to go over it now is because if I'm going to have to reverse what they said in a couple days, it seems kind of dumb, huh? So I'm just going to ignore that. So the other big way, and actually we'll go ahead and call this 2 because we're not going to pay attention to their unbounded limit thing. So we're going to ignore that. The other way that a limit cannot exist is if it's what it's called oscillating. Because the idea is that a limit is a number that as a y value that something approaches as you approach an x, but it needs to be a single y value, right? So the idea of oscillating is you don't reach a single value. You oscillate, meaning going back and forth. So you oscillate forever between values, okay? So I'm going to give you an example of something that oscillates. So we're going to go ahead and do an example. What would this be for us? It would be 5? 5. I think this is example 5. If I'm wrong, I'm sorry in advance. Okay, so I think this is example 5, but it's hard to know. Sorry, didn't mean to slide over that far. Sometimes I lose my focus. So we're going to do the limit as x approaches, let's do 0 of sine of 1 over x. Okay, so this is maybe another thing that's worth mentioning, and I think you probably already know this, but maybe you don't, so 1 over a really small number goes to infinity. Right? So you're not technically supposed to be able to do 1 divided by 0, but 1 divided by 0 is going to get infinitely large, right? So essentially, when this thing right here, so if x is approaching infinity, then if x is approaching 0, then 1 over x is approaching infinity, right? You're not actually allowed to divide by 0, but 1 over x is approaching infinity. So really what this thing is saying to you is, what's happening, so this is essentially asking, even though you're not actually allowed to say this, you're essentially asking, what is the sign of infinity? The problem is that if you look at what a sine function does, a sine function does this forever. It oscillates between 1 and -1 forever, right? So the problem is, if you think about trying to get closer and closer to infinity, right? Like, you want to have a situation where when you plug in numbers, all your values are approaching a single value. We saw this with other tables, like both sides of the table are approaching 2 or approaching 1.5 or whatever. Like, as you approach an x coordinate, both of the y values are approaching the same y coordinate. The problem is that this thing is never going to approach a value, right? Because what's going to happen is, as you get smaller and smaller and smaller numbers, right? Like, as your x values get smaller and smaller, you're going to oscillate back and forth. Like, as x goes to infinity, right? As 1 over x goes to infinity, right? Because that's what's happening. 1 over x is going to infinity. These values are going to keep going from 1 to -1 to 1 to -1 to 1 to -1 to 1 to -1. So this is oscillating. So the limit here does not exist because this value is going to keep oscillating. Now I want to contrast that with an example where the limit does exist. So if instead I asked you for the limit as x approaches infinity of cosine of 1 over x. Okay, so the trick here is that as x approaches infinity, right, 1 over an infinity is going to be 0, right? 1 over something infinitely large is going to be 0, right? That's what happens. If you have one pizza and you divide it by infinite people, nobody gets any pizza. So this is essentially just behaving like the cosine of 0, which is a 1, right? The difference here is that this quantity inside the sign is going to infinity, and so it's never going to reach a specific value, okay? And that's going to happen with any of these periodic functions that go back and forth and back and forth and back and forth, okay? So that's an example of a function that does not exist because it's oscillating. Couple quick kinds of behavior that give you things that don't exist, or limits that don't exist, right? So the three big ways that you can see it, and this is what your textbook mentions, right? So the textbook actually mentions this on page 51, if that helps, but they write it in Matthew terms because they're fancy. So the first big way that a limit cannot exist is if the left-sided limit and the right-sided limit aren't the same, right? Which we saw here. The second one they're going to mention is the one that I told you they're going to reverse in a couple sections, right? Like 3 sections later, which is that the graph goes up or down forever as you approach some x equals c, right? Meaning it's unbounded, it does not hit a boundary. They're going to reverse that in a couple sections and tell you that it's fine. And then the last one is that it oscillates between 2 fixed numbers as you approach that c. So as x approaches 0, this thing's approaching infinity, and we're oscillating between 2 fixed numbers. That would be an example of oscillating, okay? You're not going to see a ton of oscillating graphs where things don't exist, but just to give you sort of an idea. So yeah, that's kind of the deal. That's our 1.2.